250 million years ago, a group of land-dwelling reptiles ventured into the water. This seemingly simple act would set in motion an extraordinary evolutionary journey, leading to the development of some of the most remarkable creatures ever to inhabit our planet's oceans. The Triassic period marked a pivotal moment in evolutionary history. As reptiles returned to the sea, they embarked on a remarkable journey of adaptation. Over millions of years, these creatures would transform into streamlined predators, perfectly suited for life in the ancient oceans. Today, paleontologists are piecing together a fascinating puzzle. Recent discoveries are shedding light on the colossal proportions these marine reptiles achieved. A newly identified species stands at the forefront of this scientific revelation, challenging our understanding of prehistoric marine life and the boundaries of animal size. As we delve deeper into this ancient mystery, we'll uncover evidence that will change the way we view these prehistoric giants. Imagine a time when the oceans were ruled not by whales, but by reptiles that grew from humble beginnings to rival the size of school buses. What forces drove these creatures to such extreme proportions, and how quickly did this transformation occur? The story of ichthyosaurs begins in the early Triassic period, approximately 250 million years ago. These marine reptiles emerged shortly after the devastating Permian Triassic extinction event, which had wiped out nearly 95% of marine species. This catastrophic event inadvertently created an opportunity for ichthyosaurs to thrive in the newly vacant ecological niches. The earliest ichthyosaurs were relatively small creatures, measuring only 1 to 2 meters in length. However, they possessed critical adaptations for aquatic life, including streamlined fish-like shapes that allowed them to move efficiently through the water. Over the next few million years, ichthyosaurs underwent a period of rapid evolution and diversification, filling a wide range of ecological roles and developing specialized hunting strategies. By the late Triassic period, some ichthyosaur species had grown to truly enormous proportions. Shonisaurus, one of the largest known ichthyosaurs from this time, reached lengths of up to 21 meters, comparable to a modern sperm whale. These massive creatures were apex predators, dominating the ancient seas much like today's large whales. However, recent discoveries suggest even larger species may have existed. The Ostcolossus specimen, found in the UK's Westbury Mudstone Formation, hints at an ichthyosaur potentially reaching 25 to 26 meters in length, rivaling or even surpassing the size of Ichthyotitan. The success of ichthyosaurs can be attributed to several factors. Their streamlined bodies and powerful tails made them efficient swimmers, while their large eyes provided excellent vision for hunting in the dark depths of the ocean. Additionally, their generalist feeding strategies allowed them to adapt to changes in prey availability, ensuring their survival across millions of years. Recent studies suggest that the aquatic environment itself played a crucial role in allowing ichthyosaurs to reach such impressive sizes. The buoyancy of water supports larger body forms compared to terrestrial environments, reducing the physical constraints on growth. Combined with the abundant food resources available in the Triassic oceans, this buoyancy effect may have facilitated the evolution of giant ichthyosaurs. However, the story of ichthyosaur evolution doesn't end with Shonisaurus. Recent discoveries have hinted at the existence of even larger species. Fossilized remains found in the Lilstock Formation and Blue Anchor Formation of the UK have suggested the presence of ichthyosaurs that may have dwarfed even the largest known species. These tantalizing finds have opened up new questions about the upper limits of ichthyosaur size and the factors that might have influenced their growth. While scientists debated the upper limits of ichthyosaur size, nature had already provided an answer, hidden in plain sight on an English beach. What if the largest animal to ever live wasn't a whale, but a reptile that swam the seas 202 million years ago? In 2016, amateur fossil hunter Paul de la Salle made an extraordinary discovery on the beach at Lilstock, Somerset, England. He uncovered a massive jawbone fragment measuring nearly a meter long, hinting at an ichthyosaur of unprecedented size. This find, known as the Lilstock specimen, was recovered from the upper Triassic Westbury Mudstone Formation and immediately caught the attention of paleontologists worldwide. Initial estimates based on the jawbone fragment suggested a creature potentially 25 to 26 meters long. This proposed size was staggering, surpassing even the largest known ichthyosaurs like Shawnosaurus. Scientists were understandably skeptical. Could this fragment truly represent an animal larger than any previously discovered marine reptile? The scientific community's cautious approach was well-founded. Size estimates based on fragmentary remains are notoriously challenging, and extrapolations from other ichthyosaur species could lead to inaccurate conclusions. However, the Lilstock specimen was just the beginning of an unfolding mystery. In 2020, another significant jaw fragment was discovered at Blue Anchor, Somerset. This second find provided crucial corroborating evidence. The Blue Anchor site yielded additional fossils, including pieces of jaw, ribs, and vertebrae, which were carefully excavated until October 2022. With two separate locations producing similar fossils, researchers conducted a comprehensive analysis. Their findings were groundbreaking. In 2024, after years of careful study, scientists formally described a new species, Ichthyotitan severnensis. Dr. Dean Lomax, lead author of the study, emphasized the significance of this discovery. Ichthyotitan represents a pivotal moment in our understanding of marine reptile evolution. Its immense size and unique anatomical features challenge our previous conceptions of ichthyosaur diversity and adaptation. The name Ichthyotitan severnensis, meaning Titan of the ichthyosaurs from the Severn estuary, reflects both its immense size and the location of its discovery. This creature lived approximately 202 million years ago during the late Triassic period, a time when marine reptiles were reaching the peak of their diversity and size. The detailed analysis revealed unique anatomical features that set Ichthyotitan apart from its relatives. These distinctions confirmed its classification as a distinct species and hinted at its specialized adaptations for life as a giant marine predator. However, the exact size of Ichthyotitan remains a topic of ongoing debate within the scientific community. While the discovery of Ichthyotitan is undoubtedly exciting, it's important to note that the size estimates are based on extrapolations and comparisons with other ichthyosaurs. This leaves room for uncertainty and continued research. The possibility of future discoveries providing more complete specimens could refine our understanding of this ancient sea monster's true dimensions. Estimating the size of Ichthyotitan is like trying to reconstruct a giant jigsaw puzzle with most of the pieces missing. Yet, even with limited evidence, researchers have managed to paint a picture of a creature so massive it rivals the largest animals alive today. When it comes to sizing up ancient sea monsters, paleontologists face a unique challenge. Unlike modern animals that can be measured directly, extinct species like Ichthyotitan leave behind only fragmentary remains. In this case, scientists had to work with jaw fragments and a handful of other bones to determine the overall size of this colossal creature. The process begins with careful comparisons to more complete ichthyosaur skeletons. By analyzing the proportions of known species, researchers can make educated guesses about how the Ichthyotitan's jaw might relate to its total body length. This comparative method is a cornerstone of paleontological research, allowing scientists to fill in the gaps when complete fossils are unavailable. Initial estimates for Ichthyotitan's length ranged from 22 to 26 meters, placing it among the largest marine reptiles ever discovered. However, science is an iterative process, and these figures were subject to revision as new data emerged. In 2024, after several years of rigorous analysis, researchers refined their estimates, settling on a length of 25 to 26 meters for Ichthyotitan. While length estimates have become more precise, determining the weight of Ichthyotitan remains a significant challenge. Current weight estimates vary widely, ranging from 30 to 150 tons. This broad range reflects the uncertainties inherent in reconstructing an animal from limited fossil evidence. Factors such as body shape, tissue density, and organ size all play crucial roles in determining an animal's mass, and these details are often lost to time. Gregory S. Paul, a renowned paleontologist, critiqued the initial weight estimates, arguing that they were likely overestimated based on comparisons with other ichthyosaur species and modern marine animals. The debate surrounding Ichthyotitan's body proportions and shape continues to spark lively discussions among paleontologists. Different genera of ichthyosaurs exhibited significant variations in anatomy, complicating efforts to accurately reconstruct Ichthyotitan's appearance. Some may have had more elongated bodies, while others were more robust. Without a complete skeleton, determining the exact body plan of Ichthyotitan remains a matter of informed speculation. To refine their understanding of Ichthyotitan's size and structure, researchers are employing cutting-edge techniques. Histological analysis of bone structure provides insights into growth patterns and potential size limits. By examining the microscopic structure of the fossilized bones, scientists can glean valuable information about how Ichthyotitan grew and developed over its lifetime. The story of Ichthyotitan's discovery and subsequent analysis highlights the dynamic nature of paleontological research. As new fossils are unearthed and analytical techniques improve, our understanding of prehistoric life continues to evolve. The case of Ichthyotitan serves as a reminder that even seemingly settled questions in paleontology can be reopened by new evidence. As our understanding of prehistoric life evolves, so too does our appreciation for the complexity of ancient ecosystems. Ichthyotitan's remains reveal a creature uniquely adapted to its environment, with jaw features unlike any other known ichthyosaur. But what advantages did these adaptations provide, and how did they shape Ichthyotitan's place in the Triassic seas? The jaw structure of Ichthyotitan provides crucial information about its anatomy and lifestyle. Its distinctive cerangular bone, with an upward bend at an almost right angle towards the back, sets it apart from other large ichthyosaurs. Additionally, the coronoid process, which serves as an attachment point for jaw muscles, is low and swollen, unlike the pronounced processes found in other ichthyosaurs such as Shonosaurus. These unique features suggest that Ichthyotitan employed different feeding strategies compared to its relatives. The robust design of its cerangular bone indicates powerful jaw movements, potentially allowing for versatile feeding techniques. This versatility would have been a significant asset in the competitive marine ecosystems of the late Triassic period. The microscopic structure of Ichthyotitan's bones reveals signs of rapid growth and high flexibility. These characteristics might have allowed it to reach its massive size quickly and withstand the immense pressures encountered during deep-water feeding dives. The jaw anatomy also suggests adaptations for processing large volumes of water, crucial for suction feeding. The unique curvature of Ichthyotitan's cerangular bone may have enhanced its ability to capture and consume large fish and squid. While these jaw fragments provide valuable insights, much of Ichthyotitan's anatomy remains a mystery. The fragmentary nature of the fossil evidence limits our ability to make comprehensive comparisons with other ichthyosaurs and modern marine animals. This gap in our knowledge serves as a reminder of the challenges faced by paleontologists in reconstructing extinct species from limited remains. The study of Ichthyotitan's jaw structure exemplifies the meticulous work involved in paleontological research. Scientists must carefully analyze every available piece of evidence, comparing it with known species and modern analogs to build a coherent picture of an ancient creature. In this case, the unique features of Ichthyotitan's jaw have opened up new avenues of inquiry into the diversity and adaptations of ichthyosaurs. The Triassic seas were a world of extremes, and Ichthyotitan stood at the apex. But being the biggest didn't necessarily mean having an easy life. How did this warm-blooded giant sustain itself, and what surprising strategies might it have employed to thrive in a sea teeming with competitors? Ichthyotitan's massive size suggests it was likely warm-blooded, a trait that would have supported its high energy demands. This adaptation allowed it to maintain a constant body temperature, enabling it to hunt effectively in the warm, shallow seas of the late Triassic. Evidence for warm-bloodedness in Ichthyotitan includes fibrolamellar bone structure, similar to that found in modern mammals and birds, as well as oxygen isotope ratios in fossilized teeth that indicate elevated body temperatures. These adaptations would have allowed Ichthyotitan to be active for extended periods, giving it a significant advantage over its prey and competitors. The diet of Ichthyotitan remains a subject of debate among paleontologists. Its size suggests it could have fed on a variety of large marine animals, including fish, squid, and even smaller marine reptiles. However, some scientists propose a more surprising possibility. Ichthyotitan may have been a filter feeder, similar to modern baleen whales. This hypothesis is based on the unique structure of Ichthyotitan's jaw, which shows adaptations that could have supported both active predation and filter feeding. The flexible bone structure of its jaw might indicate a suction feeding strategy, allowing it to create powerful vacuums to draw in prey. On the other hand, its large size and streamlined body could have been well suited for ram feeding, a technique where the animal charges into schools of prey with its mouth open. The versatility of Ichthyotitan's feeding apparatus suggests it may have employed multiple strategies depending on the available prey and environmental conditions. This adaptability would have been a significant advantage in the dynamic ecosystems of the Triassic seas, allowing Ichthyotitan to exploit a wide range of food sources and thrive in various marine environments. The presence of large eyes in ichthyosaurs, a trait likely shared by Ichthyotitan, indicates adaptations for hunting in deeper or darker waters. This suggests that Ichthyotitan may have been an effective nocturnal hunter, able to pursue prey in low-light conditions or at greater depths. Such capabilities would have further expanded its ecological niche and hunting opportunities. While Ichthyotitan's intelligence and social behavior remain largely speculative, the lack of clear evidence for group formations or sexual dimorphism suggests it may have been a solitary hunter. However, its large brain size relative to body mass, a trait common among ichthyosaurs, hints at potentially complex cognitive abilities. These could have included advanced spatial awareness, memory, and problem-solving skills, all of which would have been advantageous for a large marine predator navigating the vast Triassic oceans. Ichthyotitan's role in the Triassic seas raises intriguing questions about its impact on marine biodiversity. As a large, warm-blooded animal with high energy requirements, it would have exerted significant pressure on prey populations. This pressure could have driven evolutionary adaptations in other marine species, potentially contributing to the diversity of life forms that emerged during this period. The warm, shallow seas of the late Triassic provided an ideal environment for Ichthyotitan to thrive. These waters were teeming with diverse marine life, offering abundant food sources and allowing for various feeding strategies. The relatively stable climate of this period may have contributed to Ichthyotitan's success, providing consistent conditions that supported its growth to such enormous proportions. As the Triassic period drew to a close, approximately 201 million years ago, a series of catastrophic events unfolded that would reshape the world's oceans. This tumultuous time, known as the end-Triassic extinction event, proved to be a turning point in the history of marine life. The once dominant ichthyosaurs, including the colossal Ichthyotitan, faced unprecedented challenges that would test their ability to survive. The end-Triassic extinction was characterized by a combination of factors, including intense volcanic activity, climate change, and fluctuations in sea levels. These environmental shifts had far-reaching consequences for marine ecosystems, altering habitats and disrupting food chains. For Ichthyotitan, which had evolved to thrive in specific conditions, these changes proved particularly challenging. As the oceans transformed, many marine reptile species vanished from the fossil record. Ichthyotitan and its massive relatives, despite their remarkable adaptations, couldn't withstand the rapidly changing environment. Their disappearance marked the end of an era of marine gigantism that wouldn't be matched for millions of years. While the largest ichthyosaurs didn't survive into the Jurassic period, smaller species managed to persist. These more modest-sized ichthyosaurs continued to thrive for millions of years, adapting to the new ecological landscape. Their survival demonstrates the resilience and adaptability of the ichthyosaur lineage, even in the face of massive environmental upheaval. The extinction of giant ichthyosaurs like Ichthyotitan left a significant gap in the marine ecosystem. The ecological niche of supergiant marine predators remained empty for a considerable time, likely affecting ocean food webs and the balance of marine ecosystems. As the Jurassic and Cretaceous periods unfolded, other large marine reptiles evolved to fill similar roles in the ocean ecosystem. Pliosaurs and mosasaurs became formidable predators in their own right, occupying similar ecological niches to the extinct ichthyosaurs. However, none of these later marine reptiles reached the extreme dimensions of the late Triassic giants, underscoring the unique conditions that allowed for the evolution of such enormous marine creatures. The story of Ichthyotitan and its contemporaries serves as a powerful reminder of the dynamic nature of life on Earth. It illustrates how even the most dominant and well-adapted species can fall victim to large-scale environmental changes. The end-Triassic extinction event reshaped marine ecosystems, setting the stage for the evolution of new groups of marine reptiles, and eventually, the rise of marine mammals. The discovery of Ichthyotitan has pushed the boundaries of our understanding of animal size. With estimated lengths of 25 to 26 meters, this ancient marine reptile rivals or potentially exceeds the size of the largest living animal, the blue whale. This comparison is particularly striking when we consider that Ichthyotitan existed over 200 million years ago, long before the evolution of modern whales. The fact that such enormous creatures evolved in both ancient and modern oceans suggests similar ecological pressures may have been at play. These pressures likely influenced the evolution of large body sizes in marine animals across vastly different time periods. Understanding these parallels can provide valuable insights into the factors that drive the evolution of marine giants. The study of ancient marine reptiles like Ichthyotitan has real-world applications for the conservation of modern marine life. By examining the ecological roles these prehistoric giants played in their environments, scientists can better understand the importance of large marine animals in maintaining healthy ocean ecosystems today. Dr. Dean Lomax, a paleontologist involved in the Ichthyotitan research, emphasizes this connection. The discovery of Ichthyotitan not only expands our knowledge of prehistoric life, but also provides crucial insights for modern marine conservation. By understanding the roles these ancient giants played in their ecosystems, we can better appreciate and protect the large marine species that are vital to our oceans today. The Ichthyotitan discovery highlights the vital role that amateur fossil hunters play in advancing our knowledge of prehistoric life. The initial find that led to the identification of this species was made by Justin Reynolds and his daughter Ruby during a beach walk in Somerset, England. Their keen eye and dedication to preserving the fossil led to a groundbreaking scientific discovery, underscoring the importance of public engagement in paleontological research. The ongoing research into creatures like Ichthyotitan reminds us that the ocean still holds many secrets. Despite centuries of exploration and study, new and surprising discoveries continue to emerge from both the fossil record and our modern oceans. This realization prompts us to consider what other colossal creatures might be waiting to be uncovered, either from the depths of geological time or in the unexplored regions of our current oceans. As we continue to explore and study both ancient and modern marine ecosystems, we're likely to uncover more surprises that challenge our understanding of life on Earth. The story of Ichthyotitan serves as a testament to the incredible diversity and adaptability of life over millions of years. It also highlights the dynamic nature of evolution and the complex interplay between organisms and their environments. The discovery of Ichthyotitan marks a significant leap in our understanding of prehistoric marine ecosystems. This colossal creature, potentially the largest marine reptile known to science, pushes the boundaries of our knowledge about animal size in ancient oceans. Its existence 202 million years ago provides a vivid glimpse into a world where marine giants rivaled or even surpassed the dimensions of modern behemoths like the blue whale. Ichthyotitan's emergence from the fossil record not only expands our comprehension of marine reptile diversity during the Triassic period, but also highlights the vast potential for future discoveries in marine paleontology. As researchers continue to explore both ancient seabeds and modern ocean depths, the possibility of uncovering more surprising giants remains tantalizingly real. This remarkable find serves as a powerful reminder that the story of life's evolution through Earth's long history is far from complete, with each new discovery reshaping our understanding of the incredible diversity that has existed in our planet's oceans across deep time.